For section 4.8, we're discussing Newton's method. Now, Newton's method is simply a recursive formula that's going to determine the roots for many functions. In fact, this is the way that your calculator determines roots, and we'll show how to do these on the calculator here in just a little bit, the graphing part. So anytime you're calculating a zero in the calculator, you're using the algorithm of Newton's method. Now, what the algorithm of Newton's method is going to do is it's going to require you to make an initial guess. And let's say this initial guess, x sub 0, the goal of that initial guess is to find the root r of this cubic equation. Now, this cubic equation could be something that's not easily factorable. It could be some irrational root r here to where you'd have great difficulty finding it. Well, Newton's method is going to be able to approximate it pretty easily. We're going to make that initial guess x sub 0. Then you're going to trace that guess x sub 0 up into the function and find the point x sub 0, f of x sub 0. Then you're going to find the slope at x sub 0 and trace that back down to the closest point on the x-axis. Well, my function here is fairly steep, so that steep slope is going to go back down earlier to the x-axis than where the root is further over to the left. So this x sub 1, that part where that hits the x-axis, that's going to be my first refined guess. You keep on doing this process over and over and over again until your value x sub n, whether it's x sub 2, x sub 3, x sub 4, x sub 12, whatever the x sub nth term, as long as it doesn't change from the previous term, then you know you're done. In this case, I really couldn't show much more than 2 guesses due to my drawing, because any other third guess would be right on the point. Notice, after that first guess, what I would have done is I would have plotted out that first guess, x sub 1 comma f of x sub 1 on my graph. Then I would have taken the slope of the graph at that point and traced it back down to my x-axis. Now, I can see that in this manner, it's not going to be a very effective format, it would be a very effective format to find that value r. After 2 or 3 uses, I'd be right on that value. Now, what you're guaranteed is that for whenever Newton's method works, as you do more and more and more guesses, those guesses are going to approach the root's value. Now, that looks intimidating when I say as n approaches infinity, the nth guess approaches r, and you think, wow, I have to do this infinitely many times. No, most of the time you're going to converge to r by several decimal places by the time you get to about your 4th guess. Sometimes it takes a little bit more than that, but never too many. Now, Newton's method is a pretty cool technique, but doesn't always work. So I wanted to show you an instance where Newton's method would fail miserably. Newton's method has a significant trouble finding the root if there's a sudden change in the slope of the function. Specifically, let's say a function that's almost vertical going through its root, and then it really flattens out on both sides of that root as you're moving up. Well, you try to take an initial guess around this value r, and whether you put it on this side or this side, that original guess is not going to give you a point where you could plug onto the function, and then the slope of the function is going to get back down. You would have to put x sub 0 extremely close to r in order for it to converge to r. In this case, the slope at x sub 0 is nearly a horizontal line. In fact, I exaggerate the slope in my red dashed line. It would really go over further to the left here. But even with this exaggerated slope going down to the x-axis here, you can see that x sub 1 is further away from r than x sub 0 was. Now, if this function went on over and I tried to plot x sub 1 on the function, it would take me even further to the right. So whenever your guesses, and it's very quick and easy to see when Newton's method isn't going to work in the scenario, because let's say the r value was 2 and you use 3 to estimate it. Your next value might be -5. Then your next value would be 10. Then -25. Then +50. -100. positive 500. It's going to diverge away from the root value. That's why I say here, values of x sub n, the nth guess, will diverge. They continually spread out from the value of r that you're interested in as n goes to infinity. Now, that's why the calculator is going to safeguard against that by requiring you to specify left and right hand bound. Let's go ahead and look at the calculator now for just graphically how these would work. I went ahead and typed in my function x cubed minus 29. I want to find the root or the zero of that function whenever it's crossing the x-axis. You'll see that I've already found a good graph here. I said let's go window -4 to 5, and then zoom 0 should handle the y value. So I hit zoom 0. The y values come in nicely, and I see my graph. Now, if I were trying to determine how to get these zeros graphically, all I would have to do is to go in here and say, well, I'm going to calculate, and I want to calculate a zero of this function. Find out when this function is equal to 0. So second calc 0. Now, please notice what I was saying. It's going to ask you to do the left bound, and then it's going to ask you to do the right bound. Well, the left bound, am I on the left side of that point? Of course I am. I hit enter. Right bound, I arrow over to the right, and I know when I'm to the right side, I'll also be above the x-axis. So I'd go ahead and click in here. Guess, I hit enter again. So that left bound and right bound is going to keep it within that region, and you'll never have this error no matter how steep your function is. And notice it's giving me a 0 of 3.072317. Okay, now I have it even more exact right here, but either way, that's a pretty nice 0 for our function. Now, I'd like to go ahead and find this by Newton's method as well. I said above that Newton's method was a recursive formula. Well, it is. Newton's method is simply saying that the next guess, the x sub n plus first guess, is just the previous guess minus the function evaluated at the previous guess divided by the derivative evaluated at the previous guess. So that x sub n minus f of x sub n divided by f prime of x sub n, it's a pretty straightforward formula. Now, let's show how it would work within this problem that we're looking at. We already know what the 0 is, but now I want to use Newton's method to find it. Well, my function was x cubed minus 29. I know I'm going to have to evaluate the function at each guess, and I need to also evaluate the derivative at each guess. So obviously I need the derivative of that function, which is just going to be 3x squared. So now, again, I said the original guess would always be given. Let's say I told you that original guess in this problem was 3. That's close to our answer of 3.07. The closer your original guess is, the faster it will converge to the actual answer. But in this case, I chose 3 as my original guess. Let's show you how I did this on the calculator. And this is by far the easiest way to show these and to do these on your calculator this way. Now, I want to get that original guess in as an answer. So I hit 3 and then enter for the answer. Now, I have my calculator on a weird float mode, so I'll go back to the normal mode. So now 3 answer. And then I want my calculator to know that I'm going to plug that answer in for x. So all I hit is the STO x. Now I'm going to hit colon. I want to type in Newton's method. Newton's method in this problem was right here. I'm supposed to put x minus the function evaluated at x divided by the derivative evaluated at x. No problem. So I'll say x minus the fraction. Well, I'll go alpha y equals for fraction. F of x. Well, I'm just going to type in my function here. X raised to the third minus 29. And then in my denominator, 3x to the second. So now, notice what the calculator is going to do. It's going to take that answer of 3, store it in for x, and then it's going to evaluate this function at that value of 3. So it's going to be 3 minus f of 3 divided by f prime of 3, which is precisely what I need it to do. So it better give me this answer. It does. So this is where I got my x sub 1 answer for. This is my first refined guess. So I know that this is closer to the actual root than my original guess was. But I don't really know exactly, unless I've already done this over here, I wouldn't know exactly how close of an answer that is. So Newton's method would have to keep going. And you say, okay, the second refined guess. Well, the second refined guess is nothing more than your first refined guess minus the function evaluated at your first refined guess divided by the derivative evaluated at the refined guess. And this is where this trick I'm showing you on the calculator comes in so handy. Instead of having to type that in each time, all you have to do is hit enter. And you think about why. This is my answer now. It's going to store that new answer in for x and then plug that into the function. So all I have to do to get to each refined guess is to keep on hitting enter. My second refined guess is the 3.07231783. Now please notice from this point to this point I can already guarantee 2 decimal place accuracy. I am 100% certain that the root is 3.07 because anytime a decimal place repeats with Newton's method, you know you're accurate to that many decimals. Now at this point, I'm not sure if it's 3.074 or 3.072, but either way, I know it's 3.07. I keep on going. The third refined guess, you'd say, well, that's going to be 3.072316826 here. And I stopped at the third refined guess here, as whenever you work the homework problems, you'll see that the book typically stops at the third refined guess. But if you wanted to keep on going, now up to this point, how many decimal place accuracy would I be insured? I would be insured 5 decimal place accuracy, because I know it's going to be 3.07231, and then I'm not sure if the next number should be 7 or 6. It's most likely 6, but I wouldn't be guaranteed that. Now notice if I hit enter one more time on the calculator, then I can see, hey, notice the reason I stopped at the third refined guess is because the fourth refined guess is going to be identical, which means the third refined guess is our accurate answer there. Now please notice the accuracy of that answer is going more decimal places than what the graphing portion of the calculator could handle. So we have a more accurate answer than what I have over here. And this was the answer using Newton's method. Now let's look at a couple more problems with this Newton's method. So again, I wrote Newton's method at the top of this page as well. It's going to be the next guess is equal to the previous guess minus the function evaluated at the previous guess divided by the derivative evaluated at the previous guess. So let's look at a very basic polynomial x squared minus 14. And I'm wanting you to find the root that's close to x sub 0, the original guess, is 3. So I'll say, okay, all of this is done internally on the calculator. I really don't have to show a whole lot through here. I just show the answers I get. Now, for this problem, the original guess needs to be 3. So please notice I'm going to hit 3 and then enter on my calculator. I'll say 3, enter. I get 3 in as an answer. I'm going to store that answer in for x, and then I'm going to hit colon. That's alpha decimal. And then once I do that, I just type in Newton's method. Well, what is Newton's method for this problem? The same thing it is for every problem. It's going to be x minus the fraction, alpha y equals enter. The numerator of that fraction is your function, which is going to be x squared minus 14. My denominator is the derivative of that function, which clearly is 2x in this case. I didn't even bother to write it on my paper. So now I have x minus f of x divided by f prime of x. We're evaluating that at 3 to get our first refined guess. We have it. So I know that 3.83 repeating is a better answer than this original guess. But now I keep on going. I can say, okay, now if I plugged 3.83 repeating into that equation, what would I get? All I have to do is hit enter. My second refined guess is going to be 3.742753623. So then I can say, okay, that's my second refined guess. Would I have any decimal place accuracy at that point? And honestly, no. I don't know if it's 3.8 or 3.7. So the second refined guess, still not a very accurate answer. I keep going. The third refined guess. At the third refined guess, I'm getting my 3.741657547. And please notice at this point, if I said, how many decimal place accuracy are you guaranteed by the time you get to the third guess? And I would say, well, 2 decimal places, because this would round to 3.743, this would round to 3.742. So to 2 decimal places, it's identical. So I would know that the root of this equation is at least as accurate as 3.74. After that, I'm not sure. The fourth refined guess, you would plug this answer into the original Newton's method, x minus f of x divided by f prime of x, and it gives you this. You say, well, 3.741657384. You're like, well, okay, now we have tons of decimal place accuracy. In fact, 1, 2, 3, 4, 5. We already have 6 decimal place accuracy guaranteed. Although this would round up to 5.8 and this would stay 5.7. But still extremely accurate. If you want it as accurate as the calculator could handle, you just do the guess one more time and you see, hey, it didn't even change at all from the fourth guess to the fifth guess. That means it converged on a root. We are 100% sure that the root of x squared minus 14 is 3.741657387 due to Newton's method. Now remember, we're using the home screen on the calculator just to save you from all of the annoying arithmetic in the problem. That's not calculus anyway. If it were the calculus, I would want you to do it. We're doing the calculus in the problem by taking the derivative of the function. But as far as just plugging the numbers in, please don't do that by hand. That's just menial work. Use your calculator to help you out. And hopefully you use your calculator in a wise manner like I'm showing you here on the home screen. Saves a lot of work and effort on these problems. So now, in this next problem for number 3, I'm asking you to use Newton's method to solve when f of x is equal to 1 minus 3x sine x. Tell me when that's equal to 0. Now, I'm telling you to use an initial guess of 7. That's saying, well, the root's probably somewhere around 7. Find out where it is. Okay, so I need to go ahead and say, well, here's my function. I need the derivative of that function. So when I took the derivative, of course, derivative of any constant is 0, but the derivative of the second term required the product rule. I said derivative of the first is negative 3 times the second, and then plus the first, which was a negative 3x, I just put minus 3x, times the derivative of the second. Derivative of sine is cosine. So I have my function, I have its derivative. So Newton's method is pretty quick, should be pretty easy. I'll plug 7 in as my answer, 7 in as an answer. Please make sure that you do that first step. You always have to get what that original guess in as an answer. That's a key. A lot of students want to say 7 store x. That's terrible. That will only give you the x sub 1 over and over and over again. We need to get 7 as an answer. Now we need to store that answer in as x, colon. Now we type in Newton's method. Every single time it's x minus the fraction f of x. Well, that's 1 minus 3x sine x in this problem. And my denominator was negative 3 sine x minus 3x cosine x. Now, something that would probably be wise to check in this problem, I'm pretty confident that mine is in the correct mode, but you would want your calculator to be in radian mode. Often for several of you students, you're in engineering and applied classes to where you use degree mode quite often too. Make sure you're in radian mode for these. Now, when I try to find the answer for x, I'll say, well, my first refined guess. I'll get my 6.281200622, and I know that this is at least closer to the actual root than my original guess is, but I don't know how many decimal place accuracy at all. I hit enter. That's going to plug this first refined guess back into Newton's method, And when I do that, you'll see I'm getting 6.336271226. At this point, I still don't have any decimal place accuracy. I guess you could say, well, no matter what, it's going to round to be 6.3. So yeah, you could say 1 decimal place accuracy. To get the third refined guess, we just simply hit enter again, and I'll get the 6.335820552. And now I know I have, goodness, notice 3 decimal place accuracy. To 3 decimal places, this would be 6.336. So would this. But let's say that that's not good enough. I keep on going. By the fourth refined guess, I can say it's 6.335820526, and now I know that this is going to be accurate, it looks like, to 7 decimal places. I went ahead and went as far as the calculator could handle before every one replaced. And you can say, well, if you want to be confident to I guess that's 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. If you want to be confident to 9 decimal place accuracy, you have shown that by the 5th refined guess. As soon as it repeats itself, you know it's accurate to that many decimal places. Okay, now, hopefully you're thinking this is pretty straightforward stuff. Now, one thing I do need to mention about all these functions up here is that please notice these functions I was giving you, I was finding the root, or finding when the function is equal to 0. Newton's method only finds roots. So you're going to have a differentiable function set equal to 0. I mentioned that now because I'll be asking you to find the 60 to the 1/4 power using Newton's method. And I don't just simply want to go in and say, well, hey, I don't need Newton's method for that. I can just go to my calculator and say that's 60 raised to the 1/4 power. There you go. Woohoo! Well, no, that's not good enough. I mean, that is the correct answer for what that value is, but I want to use Newton's method to get to that. So with Newton's method, I need to have a differentiable function that has a variable derivative, not a constant derivative, and that I can set equal to 0. So when I'm thinking, well, what do I do if I have something like 60 to the 1/4 power and I'm asked to use Newton's method? Well, I can say the root I'm looking for is x is equal to 60 to the 1/4. But now I don't want x equaling 60 to the 1/4, because if I tried to move that over and say, well, then f of x is x minus 60 to the 1/4, the derivative of any linear function is just a constant. I can't work with that. So what I went ahead and did is I got a function here by saying, well, let's take both sides to the 4th power. That would get rid of the 1/4 power, and it gives me a nice x to the 4th on the left. Now, if I move the 60 over to the left side with the x, I'd be finding the roots of this equation. So I'm trying to find when f of x is equal to x to the 4th minus 60, trying to find when that's equal to 0, and that's going to be solutions to the original problem. Now, this is the first equation that I can actually work with because, yes, it's going to have a differentiable derivative. So derivative of x to the 4th is 4x cubed. I'll use that function and I'll use its derivative in my Newton's method. I'll say, okay, 60 to the 1/4 power, I was thinking the way I got that original guess of 3. Now, again, remember, you're going to be given the original guess, but I just thought of that in my head. I said, well, I know 2 to the 4th power is 16, 3 to the 4th power is 81, 60 is closer to 81 than it is 16, so this has to be closer to 3 than it is 2. My answer has to be close to 3. So I just said, well, let's let the original guess be 3. So I went in here and said, okay, 3 store x again. Oh, no. That's what you don't want to do, guys. Sorry. 3, get it in as an answer. Please remember, get whatever your original guess in as an answer. Now you store that answer in as x and colon alpha decimal. Type in Newton's method for this problem. As always, it is x minus the fraction, alpha y equals fraction. You're going to put the f of x in the numerator, so x raised to the 4th minus 60 in the numerator. Your denominator is the 4x cubed, 4x raised to the 3rd. You say, well, what's your first refined guess? It should be 2.805 repeating. Boom. Yes. So you can say, we know that that's actually closer to the answer of 60 to the 1/4 power, and we actually know that because we found it's 2.7831 up here as well. But my first refined guess that I get with Newton's method is this. Then Newton's method is going to say, well, if you keep on doing this, it should converge on the actual root. And again, remember, this is how your graphing calculator determines it within the graphing portion. I'm going to get 2.783424476. So I can say, okay, at this point, I'd be guaranteed 1 decimal place accuracy. Whether I'm looking at x sub 1 or x sub 2, I could say, well, it's at least 2.8. If I keep going to get to the third refined guess, now I have 3 decimal place accuracy. I know it's 2.783. After that, I'm not certain. The fourth refined guess, I can say, well, it's going to be 2.783, and then notice 157. It's all exact up to that point, and then the next digit could be a 7 or a 6. But then we quickly see that this fourth refined guess was the actual value to 9 decimal places, because the fifth refined guess doesn't change a bit. So it's converged on the answer. Now, hopefully this technique of Newton's method makes sense to you. It's a really neat recursive technique. Your calculator can be a great assist on this. Now, while we're doing this all on the calculator, please don't think we're gypping you of any calculus. I'm not. If we were, I wouldn't be doing it on the calculator. The only thing that we're saving you is just arithmetic, plugging it into the function, and that's needless time-consuming effort. So if you follow the way that I did this on the calculator, these problems should be super quick and hopefully super easy. Let me know if you have any questions. I'll be glad to help.